Next report, Einstein solvmanifolds not based on nilsolitons by Federico Rossi. Please.
Okay. Thank you. I would like to thank the organizer that gave me the opportunity to talk about my research today. In this talk, I will describe a new method to obtain indefinite Einstein solvmanifold that are not based on nilsolitons. This is a joint work with Diego Conti and Segnan Dalmasso. So I will start by recall some property of Einstein metric in the homogeneous context. I will deal with invariant structure on solvmanifold. Then I will describe some property of the pseudo-Riemannian case. And finally, I will describe how to construct some new examples that are not based on nilsoliton and which are not pseudo-Iwasawa. So, one of the most classical problems in geometry is to find and study special metric. Among them, one of the most interesting are the Einstein metrics, which are important for connection with general relativity, and they are, for example, a fixed point for the scalar curvature, a Mangold metric with a fixed volume. But in general, this problem is difficult to study because they are partial differential equation of the second order. An Einstein metric is a metric such that the Ricci tensor is a multiple of the identity. If the multiple is the Ricci tensor is the zero, we call the metric Ricci flat. If we restrict to the homogeneous case in the Riemannian setting, the things are well understood. We have a tripartition depending on the sign of the scalar curvature of the Einstein metric. And moreover, there is a theorem now by Bohm and Lafuente, which was a long-standing conjecture by Alexievsky, that say that all Riemannian homogeneous Einstein manifold of negative scalar curvature are indeed solvmanifolds. Solvmanifold is a simply connected solvable Lie group together with a left invariant metric. So, yeah, let me fix the setting where we are going to work. We fix a Lie group together with a left invariant pseudo-Riemannian or Riemannian metric. This is equivalent to define a bilinear non-degenerate form on the Lie algebra. And so all the Levi-Civita connection, the Ricci and the Riemann curvature can be seen as a tensor on the Lie algebra. Now, in the Riemannian case, we have that the Ricci flat condition is equivalent to have the unimodularity of the solvmanifold. And moreover, if we have an Einstein solvmanifold, then it split as the orthogonal sum of n and a, where n is the neoradical of the solvable Lie algebra, and a is a subalgebra, which is abelian. Moreover, the metric, Einstein metric, restricted to the neoradical part, define a nilsoliton equation. That means that the Ricci is a multiple of the identity plus a derivation. This derivation is quite particular because satisfy this condition with respect to any other derivation, and is called the Nikolajewski or pre-Einstein derivation. It is diagonalizable, and when we have an Einstein solvmanifold, it has a positive rational eigenvalues. The solvmanifold Einstein determines the metric uniquely on the neoradical. And this also works on the converse. If we have a nilsoliton metric, we can extend it to an Einstein solvmanifold. And this extension is unique up to the isometry. Those are all results by many authors, such as Lauret, Hebert, Nikolajewski. So we have that the classification of Einstein solvmanifold is the same as the classification of nilsoliton in the Riemannian setting. Now, what happened in the pseudo-Riemannian case, in the indefinite case? Well, we don't have a tripartition in the homogeneous setting. We have examples of Ricci flat that are not flat or nor compact nor unimodular. If we restrict to the nilpotent case, in the Riemannian setting, the only Einstein metric is the one that you have on abelian nilpotent Lie algebra. But we are able, together with Diego Conti, to construct some example of indefinite Einstein metric with scalar curvature different from zero on non-abelian nilpotent Lie algebra. We also find some obstruction to the existence of those metrics. Those metrics were constructed on some special nilpotent Lie algebra called nice nilpotent Lie algebra. So let me recall what are nice nilpotent Lie algebra. We have a basis on a nilpotent Lie algebra called a nice basis if the bracket of element of this basis are a multiple of other element of this basis up to a constant. And then moreover, the structure constants Ci, K are completely determined by any true values of Ij or Ik. Those notion of nice nilpotent Lie algebra were introduced by Laurette and Will in the study of nilsoliton and Ricci flow metric that we also listened some talk before about the Ricci flow. Moreover, we use those nice Lie algebra to construct explicit left invariant Einstein metric which have the scalar curvature different from zero. Now, those nice nilpotent Lie algebra can be linked with a diagram. Namely, to any nice nilpotent Lie algebra, we can associate a diagram delta, where any node on the diagram is defined by the element in the basis, and we add some arrow when the bracket of two elements of the basis is different from zero. So those diagrams are direct, are cyclic, and without multiple arrow. And we can construct those diagrams in a combinatorical way. Moreover, we can associate a root matrix M delta that has many rows, has many different bracket non-zero we have in the structure constant in the equation of the nilpotent Lie algebra. So here you can see some example of Lie algebra and the associated nice diagram, let's say. Moreover, those nice Lie algebra has some important feature. If we fix a nice nilpotent Lie algebra with a diagram delta, and we fix a diagonal metric with respect to the nice basis, then the Ricci tensor is completely determined by a vector x and the root matrix M delta. Moreover, the vector x is related to the constant structure and to the metric with this exponential map, which is namely the exponentiation of the root matrix M delta. We also use this notation for log sign for some vector, which will be useful in the sequel. Now, in the pseudo-Riemannian setting, we also have the notion of nilsoliton. Nilsoliton is a nilpotent Lie algebra together with a pseudo-Riemannian metric, such that the Ricci tensor is a multiple of the identity plus a derivation of the Lie algebra. We prove that in the pseudo-Riemannian setting, the derivation D may not be the Nikolaevsky derivation. So we have a first difference from the Riemannian case. Moreover, we find that this equation, the nilsoliton equation, can define four different nilsoliton type of equation, depending of if the lambda or D, the derivation are zero or not. We also find that all those examples can happen in the nilpotent, in the pseudo-Riemannian setting. So if we want to study Einstein solvmanifold starting from a nilpotent ideal, we need some decomposition. So we say that a solvable Lie algebra has a standard decomposition if we have an orthogonal decomposition, direct sum, G plus A, where G is a nilpotent ideal and A is an abelian subalgebra. The standard, the Riemannian submanifold Einstein are standard for this definition, but we do not require that the nilpotent ideal to be the nil radical. We also make this definition. We say that a standard decomposition is said to be pseudo-Iwasawa if the adjoint for any element in the abelian part is symmetric with respect to the metric, the pseudo-Riemannian metric. Now, why the first definition, the standard decomposition, is needed if we want to study the extension and relate the extension, the Einstein extension, to some property on the abelian nilpotent ideal, because if we do not require the standard decomposition, we have that the pseudo-Riemannian metric may be degenerate on the nilpotent ideal. On the other hand, the second definition, the pseudo-Iwasawa, is not required. We have a lot of examples of Einstein submanifold in the pseudo-Riemannian setting which are not pseudo-Iwasawa. Moreover, however, this definition is natural if we want to find a relation between the nilsoliton equation and the Einstein submanifold, such the one that we have in the Riemannian setting. So we were able to construct this relation. For example, if we have a pseudo-Iwasawa decomposition, then the Einstein condition is equivalent to require that we have a nilsoliton equation on the nilpotent ideal, and but we have some difference because the derivation D may not be the Nikolaevsky derivation. But this correspondence works very well if we require that the Einstein metric has a non-zero scalar curvature. In this case, we have a very well relation between the pseudo-Iwasawa Einstein submanifold with the scalar curvature different from zero and nilsoliton metric on the nilpotent ideal with where we mean nilsoliton of type nil4, the one with the derivation which is not zero. And also on the converse, if we have a nilsoliton equation where the lambda is non-zero, then we are able to construct an extension which is Einstein solvable and which is of the pseudo-Iwasawa type. However, as I said before, this definition is quite restrictive because, for example, if one want to construct some Sasaki pseudo-Riemannian metric, which is also Einstein, then we don't have any pseudo-Iwasawa decomposition. So we need some change in this definition and some different technique to construct those examples. For example, for the pseudo-Iwasawa case, we use this definition, the zeta standard Sasaki structure, which is a Sasaki structure with some more assumption, namely that there are some vector E0 and some element in the center that satisfy those B, that satisfy those extra conditions. These Sasaki structure, pseudo-Sasaki structure, are related to the Keller reduction in a natural way. And moreover, those relation is well defined if one consider a zeta standard Sasaki structure of dimension n+3 with a Keller reduction of dimension n. So we are able to find and to construct those extension, which are zeta standard Sasaki, starting from a pseudo-Keller nilpotently algebra of dimension n-3, together with a derivation, the check, that must satisfy some technical assumption. However, adding some very few examples, some very few conditions on this derivation, such that the symmetric part is plus or minus the identity, and some assumption on the constant h, we found that this zeta standard Sasaki structure is indeed Einstein. So we are able to find this characterization of zeta standard Sasaki-Einstein structure, which can be constructed starting from pseudo-Kähler nilpotent Lie algebra of dimension n-3. Using those results, we are able to classify in low dimension some pseudo-Iwasawa example, mainly arising from nice nilsoliton of dimension up to dimension 9 for the Riemannian nilsoliton metric, but also up to dimension 9 with some more restriction. Here we, by classification, I mean that we are able to solve the nilsoliton equation when we have a diagonal metric which is diagonal to respect a nice basis on the nice nilpotent Lie algebra. But we also construct some non-pseudo-Iwasawa example. The first one were the ones arising from the nilpotent Einstein metric with the scalar curvature different from 0, but also those the ones that arise from the zeta standard Sasaki-Einstein Lie algebra. In particular, we classify all the dimension less or equal to 7, and in any dimension with the Kähler reduction, which is an abelian Lie algebra. However, if one wants to construct something more general, we have to deal with the so-called generalized nilsoliton equation. So in this case, we have a rank 1 extension of an nilpotent Lie algebra, which is Einstein. Then the restriction of the metric to the nilpotent ideal must satisfy this generalized nilsoliton equation. Note that if the derivation D is symmetric, then we recover the usual nilsoliton equation that we studied before. We are also able to construct a solution, particular solution to this generalized nilsoliton equation when we have a derivation that is diagonal plus some extra terms outside of the diagonal. Those extra terms are indexed by this subset A with the assumption that two element AJ, pair AJ in the set A are all pairwise distinct. Then the generalized nilsoliton equation is equivalent to satisfy those system of those equation plus some assumption on the trace of D and some assumption on the non-diagonal part of the derivation. So let me explain with an example how to use this lemma. So let's start with a 4-dimensional nilpotent Lie algebra. Here this is a short to say that we have a basis E1, E4 such that the dual basis E1, E4 has the Chevalier-Lambert differential that satisfies those equations, namely the differential of E1 is equal to the differential of E2 and is equal to 0. Differential of E3 is E1 wedge E2, and the differential of E4 is E1 wedge E3. Then the generic diagonal derivation has this form, and we set the extra diagonal derivations numbers as in the position, let's say 1, 2. So the generic derivation that we consider has this form, and we must solve those conditions arising from the lemma. This is a linear system in the element A in the diagonal of D and in the element uppercase A. But the uppercase and the lowercase a are related by a quadratic condition, which also involves the metric. Now we have a nice nilpotent Lie algebra together with a diagonal metric, so we know how to compute the Ricci, and the Ricci is related to some vector and to the vector x and to the delta matrix. So we solve and we found the vector x, which must be compatible with the metric. So we have that x must satisfy those equation involving also the metric. So we have those equations which are quadratic, and we found a particular solution to this equation. So we have a Lie algebra of dimension 5, which is solvable, non-unimodular, with the Einstein metric with scalar curvature different from 0. But the problem is that in this way, we have to deal with a quadratic equation, which arise from the compatibility between the metric, the diagonal metric, and the vector x, and the non-diagonal element of the derivation, lowercase aj. So the idea is to let the constant structure vary and not fixed, but fix the metric to be +1 or -1. So we fix the nice diagram with an orthonormal nice basis, and the problem becomes linear in the uppercase A and lambda, the diagonal part of the derivation, and in the entry of the vector x, but is quadratic in theCijk, but which must satisfy the Jacobi condition, the compatibility with the metric, and this other condition between the lowercase and uppercase a. So we add some this technical definition, non-diagonal triple, which is a derivation D, which is a linear map, and some subset of index that must satisfy those conditions, namely the condition of the previous lemma. And together with this definition, we are able to construct some solution to the non-diagonal triple, to the generalized nilsoliton equation. Namely, we have to solve this star condition, which is linear in x and a and lambda, but we have some extra condition involving the CI, the structure constant, together with some compatibility between the sign of the metric and the sign of the vector x. Now, let me say briefly that there is a notion of equivalence when we have two extensions that arise because the nice diagram has some automorphism of the nice diagram, which can give rise to some the same extension. So we say that two extensions are equivalent if we have a Lie algebra isomorphism, which is also an isometry. This is equivalent to the action of the out delta, the automorphism of the diagram, the nice diagram, and to the change of flipping of the sign of some element in the non-diagonal triple. So we build an algorithm to construct a non-diagonal solution up to equivalence on nice Lie algebra of dimension 9. Let me focus that up to line 5 in this algorithm, we don't have any quadratic equation. So those algorithm is linear, and the quadratic problem appear only on line 6. Moreover, condition N4 and N5 of the non-diagonal triple are defined in an unique way, the diagonal part of the diagonal metric, but the non-diagonal part may be depending on some parameter. So the application is that we are able to classify up to equivalence all the solution of generalized nilsoliton equation that rise from a non-diagonal triple on any nice diagram of dimension less or equal to 5. With the extra assumption that we don't have any parameter on the element of the diagonal of the derivation, and we don't have any parameter on the structure constant, then we are able to classify up to equivalence all the solution of the generalized nilsoliton equation up to dimension 9. So here I put the number of the solution that we found. So moreover, we show that in low dimension up to dimension 4, these new examples are not isometric to any pseudo-Iwasawa-Einstein solvmanifold that we can obtain extending some nilsoliton on a nice orthonormal basis. So those constructions are, in fact, unique and new. Here I put the table for the low dimension in dimension 3 and 4. Here we have the nilpotent Lie algebra, the non-diagonal derivation, and the last column is the set of negative element in the diagonal metric GI. So I'm out of time, so I will stop here, and I will thank you for your attention. Thank you very much.